We're going to talk through the equations in chapter 14 real quick, and we're actually going to start with the second one. And so in the second one, you have a coil over here, call it coil 1, and you got another coil over here, call it coil 2. So here's 1, here's 2. And if you run a current, an oscillating current or a changing current through this one, you get a voltage over here, and vice versa, right? So this second equation says, quite simply, the EMF induced in circuit number 1, or coil number 1, is minus, again, as in the previous chapter, we're opposing changes, so the minus sign ends up there, minus what we call the mutual inductance, times the derivative of the current over here in 2 with respect to time. Right? So a changing current in the second coil produces an EMF in the first coil. This is really essentially how FM radio works. You've got a coil that's your receiving antenna. The broadcasting antenna is a coil. This is how the cell tower and your phone communicate at some level. You could think of it this way. So you've got to have changing current with time to produce a signal on the other side. But here's the thing about mutual inductance, and the reason it's called mutual. If we look at the flux in 2 due to 1, the number of turns in 2, the current in 1, that's equal to the number of turns in 1 times the flux in 1 due to 2 divided by the current in 2. So there's a symmetry. This mutual inductance is the same for E1 equals minus M di2 dt as it is for E2 equals minus M di1 dt, right? So we can write the other equation, E2, right, is minus M di1, right, dt. Right? So both of these hold, and it's the same M, right? That M and this M are exactly the same M. That's why it's called a mutual inductance. And there's a symmetry in this relationship. They're tied together by this mutual inductance. Self-inductance. So here's the next step in this. When you take a coil, all right, take a coil, and you start running a changing current through it, running current through it, it produces its own flux, right? So depending on the number of turns, the flux, the magnetic flux, you get this term here, this L, that is a self-inductance. And the EMF produced by that self-inductance, right, is exactly the same form as the EMF produced by mutual inductance. What is this saying? This says, if I have a coil, this is just a coil of wire, right? It has N turns, it has some self-inductance L, and if I'm changing the current in this wire, I actually get an EMF in this wire, in this set of coils. And the point behind the EMF, and what the EMF is trying to do, is oppose the change in the flux going through this, right? The minus sign again, it's opposing this change. So if current is flowing this way, right, or increasing that direction, the EMF is going to be trying to drive current the other way and keep current from increasing in that direction. If we look at the self-inductance of a long solenoid, it's very straightforward. Mu naught N squared A, the cross-sectional area of the solenoid, times L, the length of the solenoid. Toroid is, you'll see toroid sometimes in radio appliances and things like that. A toroid is a loop that goes around. You got a loop of wire that ends up forming a circle. It ends up forming a circle, right? So here is your toroid. You'll see that in some radio appliances. where you're trying to get really high inductance, because it lets you get to an inductance that's dependent on the ratio of these radii. You can just tune the inductance a little bit better in a tight space than you can with a straight solenoid. Energy stored in an inductor, 1/2 times the inductance times the current going through it squared. That's all stored in you can think of that as being stored in the magnetic field. That's energy stored in the magnetic field created by the inductor. Current is a function of time for an RL circuit. So this is a circuit in which you've got some source. All right, there's a switch, and then you've got a resistor and an inductor. All right, so you've got R and L, and when you close this switch, current starts to flow, but not immediately. It behaves this rule here, where the current as a function of time is the EMF imposed from here over the resistance onto 1 minus e to the minus t over tau L, and tau L is the time constant for the RL circuit. Tau L is just inductance over resistance. Inductance, by the way, is in henries. A henry is an ohm second. Resistance is in ohms. So this gives you time, right? L over R is the time constant for the circuit. If we have charge oscillating in an LC circuit, an LC circuit is just that. You know, you've got you have on one side an inductor, and on the other side a capacitor. And what happens is, if you've got this charged up to some charge Q, Q naught, right? And you let things start running, you close a switch so this circuit is completed. Well, over here you got energy stored in the electric field, the current starts flowing, and it slowly stores energy in the magnetic field here. And when you hit zero charge over here, you've put all the energy over here, and then it keeps the current flowing until you've completely reversed the current, the charge on the capacitor. So if it was plus over here, well, after it gets through, it'll be plus on this side, and then the whole thing starts over and it starts discharging, and the inductor keeps the current flowing until it completely charges again. So the current will go back and forth. The current goes back and forth and back and forth and back and forth, and the charge on this as a function of time can be written as a cosine, Q naught cosine omega t plus phi. Phi is just an offset angle with when you started this with respect to 0. And that omega, the oscillating or the resonant frequency of this circuit, is the square root of 1 over LC. And you can see from this, LC is 1 over a second squared, right? If you look at the current in this circuit, the current, which is this dq dt, is minus omega q naught, right? It's times the sine. And then charge is a function of time in an RLC circuit. Slightly different. All we're doing is we're sticking a resistor in here, and what's happening is every time it goes through its oscillation, the resistor is bleeding energy off as heat, right? Because remember, resistors convert electrical current to heat. And so you lose energy every single oscillation, and that gives you this exponential decay term in here, minus RT over 2L. And then the oscillation frequency is a little different. It's not square root of 1 over LC. It's this term, square root of 1 over LC minus R over 2L squared. All right? So all a little different when you got the resistor in there. This is a damped circuit, right? It's a damped circuit. This, when you got just an LC circuit, it's undamped. And that's it for our review of equations for Chapter 14.